Okay, I am sorry about the issues with the recording or whatever, but it's late, but we're ready to start finally. So, how many of you, very quick poll, how many of you were here last week when we started talking about mechanistic interpretability? Quick show of hands. See, I guess about 50%. So, I'll very quickly just go over the important takeaways from the last time we spoke, because this is kind of a continuation of that entire thing. Also, please feel free to come a little bit closer so I can shout a little bit less. That will help me quite a bit. Yeah, cool. So generally the module or whatever you want to call it consists of two papers, circuit analysis and monosemanticity. Both of them are focused on understanding transformers and the attention mechanism. So there are like three main things that we're going to be talking about: background and intuition, circuit analysis, and monosemanticity. We discussed the majority of circuit analysis last week, so I'll just cover the main takeaways from it and the final result analysis, and then we can dive into monosemanticity. Before that, very quickly, just a little bit about the background. So, interpretability, to put it very lightly, is just, or to put it very simply, is the degree to which we can understand the decisions that are made by a neural network. A lot of times, the decisions that are made are black box in nature, and understanding them is quite a challenge. Mechanistic interpretability, which is the subfield that we're going to be talking about today, tries to achieve this by identifying or by reverse engineering the neural network. We treat it almost like a binary where you can run it and get inference, but the internal features are obfuscated to a certain extent. And mechanistic interpretability seeks to reverse engineer those features, and we use that in order to make some inferences about the model so we can better understand why it makes certain decisions. So that's interpretability. The architecture that we were studying for circuit analysis is as follows. We have a single layer of just attention with no multi-layer perceptron following it. The idea is that this is a toy model. We are not even including the non-linear layers outside of the one that is used for the attention mechanism. And the objective is that we can mathematically decompose this model, right, very easily as compared to that of a more complicated model, and build inferences on top of this model. So a lot of what we discussed last week was those inferences on the model. This is useful because we can do exactly that, right? We can abstract away some degree of complexity and make it a little bit more straightforward for us to understand. So where's my pen? Okay, I will find it. Anyways, so mechanistic interpretability, as I mentioned, it seeks to reverse engineer neural networks. That's like the one sentence definition of it, and that's what's basically the most important. Okay, so does this make sense to everyone, or are there questions? Thank you so much. Also, very importantly, please keep asking me questions. If there is something that you do not understand, assume nobody understands it, and I want to keep answering as many questions as possible. That is ideal for me. So that helps us all understand as well simultaneously. Anyways, are there any questions up to this point? To the two concepts we discussed were mechanistic interpretability, or actually we just, and the architecture that we're using. Okay, I see no questions, so I'll proceed. So the idea behind circuit analysis, right, the high level, is that we reformat the attention mechanism into tensor operations. So I'm going to skip ahead to the refactorization that we obtain at the very end, and it is this, right? We get these two equations, equation 10 and equation 15, and this is sort of a refactorization of the process of obtaining attention. Usually, if you were to write something like, a regular MLP, I have, wait, let me see if everything is visible. And zoom. Okay. All right. So let me know if it's not visible or needs help. All right. Okay. So if we were to just use like a normal linear regression surrounded by a activation, we would get an equation that's kind of like this. Sigma over here stands for, oh, yes. Oh, yeah, I see it. Sweet. I guess this is much better. Okay. Thank you so much. So we have this very sort of simple set of equations where we use a weight matrix x, which is our input, and then plus b, and then we create another output that uses y as input, and we kind of create this sort of equation over here, and the set of equations. This is kind of like our linear layers, where one layer is y. I'm going to name it 1, so y sub 1, and then we go to y sub 2, and the initial input is our x. Okay, so it's kind of two layer model that we are kind of simulating over here. Now we can refactor this entire thing as a single equation if we put y equals sigma, and then we put okay, let's see, w, and then another sigma, and then w x plus b, and then plus b over here, and close that, right? So it's kind of like a recursive definition that we're unlocking. And if we have a very, very long set of, like a very big or deep neural network, we will have this equation unpacks into very, very complex equations, right? It's not something that's easy for us to understand. Now, this matrix form is kind of a very significant simplification of the equation that you guys are seeing over here. So that's kind of the general idea that we are aiming at. Now, this is important or very useful for a couple of reasons. First, we can make observations about these two equations. Okay, actually, other questions about the two equations. The T stands for the full transformation, so getting the output from the input, and A stands for just attention. Every A raised to H is for attention for every single specific head. So the weights change, but functionally the equation is exactly the same. Do these two equations make sense? Yes? No? Okay. I see a thumbs up, couple of thumbs up, so I'll move forward. Awesome. So we can make a couple of observations about this. So first we have the W sub U, W sub E. This is the unembedding matrix and the embedding matrix. W sub U is unembedding to basically reverse the matrix from the dense state to the sparse token state. And W sub E does the opposite. It takes sparse tokens and converts it into dense embeddings. And this basically is the residual layer of the architecture, and then from there the second part of the equation is just all of the heads, and we can make some interesting inferences about it. First, it's a much simpler reconstruction, which I think I've stressed already at this point. A is the only nonlinear operation, or attention is the only nonlinear operation, because that is the only thing that has the softmax activation function. Rest, everything, it's a linear equation. We can technically compose it into just one single matrix. Now, this is very important because it lends to our definition of circuits, which I will show you in a second. And in addition, A, or attention, learns independently from the rest of the tensor equation. Question, please. Oh, question.
What is WU and WE again?
WU is the unembedding matrix, WE is the embedding matrix. So if we go back to the starting, we have this what do we say, architecture, correct? And we can restructure all of these operations in a more mathematical way. We covered this earlier, but I should draw this. Thank you for letting me know. So I am going to take input tokens. I'm going to call this T sub 0. And I am going to sort of rebuild this architecture, but with the weight matrices included, so that is kind of more understandable. So we have W sub E, which is our embedding matrix, and yeah, okay. W sub E T0, which I am going to name X sub 0. And then now we go into our attention heads. So I go from here all the way to this bottom. This is going to be the residual layer. and then from this I split it into multiple heads. So in our analysis we will have 3 heads, but over here I will only show 4. So we have h sub 0 and all the way to h sub 4, but the equation that it is performing internally is our attention operation. So it's calculating multi-headed attention over here on input x0. Okay, once that is computed, it is all concatenated into the final multi-headed, or like the final attention vector, and added to the residual layer, right? Then from there we have this attention output ready, and we unembed this into x1, which is equal to w sub w sub u, and takes as input, let me call actually this, I'll call it x1.5 because I already named x0.5 because I already named this x1, and take this x0.5, and this is effectively our final output because this gives us the output tokens. So that's the general idea. If you want to process them as logits, we will compute just the log probabilities and get what we call logits. But for our analysis, this diagram is really relevant, and then the weights over here are also relevant. So in addition to these multi-headed attention, if we decompose this, we have a couple of additional weights that are also important. I won't dive into attention right now because that became a huge discussion and we are a little bit short on time, but just take this for granted, okay? We have a couple of weight matrices. We have W sub O, which is the output matrix, W sub K, which is the key matrix, W sub V, which is the value matrix, and finally W sub Q, which is the query matrix, okay? So in the computation of attention, the WQ and WK creates the attention matrix that determines how much weight has to be placed on the output dimensions from the whatever input, right? The area that we want to focus on basically. And W sub O, W sub V is the linear transformation of the base distribution to the output distribution for all of the tokens. Then we select the subset using W sub K and W sub Q. And these fundamentally actually form circuits, which is what we will discuss exactly right now. So we were over here where we had 10 and 15. We discussed these couple of things, but there is one thing that we are missing, and it's the fact that these things form a circuit. So we have W sub U all the way to W sub E, and W sub E transpose all the way to W sub E again. These are very important because if we're going to combine them into a single matrix, which we can do since these are just linear operations. Usually we can't because we add non-linear activation functions, but we are not doing that for simplicity. So these create vocabulary or number of the vocabulary. So if you have 10,000 words, it creates a 10,000 comma 10,000 size matrix, right? And this is very relevant for an eigen decomposition, which we will talk about in a second. But at a high level, these are our circuits, and they are at the heart of the transformer architecture. This is the bulk of what makes the transformer architecture so powerful. Okay, we obviously stack multiple layers of attention, but for our analysis, just this also gives us very, very interesting things to look at. The first thing is our output value circuit, right? And we show that with the set of equations. It determines how attending to a token affects logits, which is the transformation of the data distribution from the original embedding space to this new embedding space that considers the entire subspace. This is trained with the output and the value parameter matrices. Then the query and the key circuit is basically just our attention. It determines which tokens are important and which ones should be attended to. Cool. So now a diagram so that we can actually visualize this. We have a source token over here. So this is like an input sequence. The destination is an output sequence, and the output is the result. So if you want to sample this model out regressively, we will create an output. We initialize a DST or a destination token as like the start token. We have our source input, which we basically cycle through from the first one all the way to the end and create an output. We get the first output and append it to our destination, then move to the second source token and repeat this whole process until we have gotten our end token. Okay, so we can see these two colored circuits where one circuit, which is the which is the value and the output circuit, right, or the output value circuit, it connects the source token to the output token, and then there is the pick circuit. This circuit is our attention circuit. Now this circuit connects source and destination, but in a different way. So our pipeline for the matrix multiplication is kind of starting at source and finishing at output for the base line, correct? But for the pick line, it is different because we have the transpose as well, which basically means we have to interpret it in the reverse direction. So if we look at these again, we have W sub E transpose, W sub Q transpose, which we take as sort of starting from one direction, and then W sub E, W sub K, which obviously we will read from right to left because that's how we normally read matrix multiplications. Since there is transpose, we can read left to right, right? So we read right to left to right, and the output effectively meets somewhere in the middle. And that is our second circuit, which is query key. Does this make sense, or are there questions for me at this time? No questions? Okay, cool. So now we can use this information of, or like our interpretation of the circuit to interpret the model as a skip trigram. So if we just consider a single source token for simplicity, this is the kind of output that we get. So last week we had discussed this case for pigram models, where I have this sentence where we go, Bob said, and then this huge sentence or a huge paragraph, and then we ask it a question. So this is like our context, and we ask this language model a question. We ask, who said the above statement? Okay, I'm going to skip above because I'm lazy. Who said the statement? Okay, now the answer is Bob. Okay, we know this just kind of evidently, but for a language model to know this, it needs to take like a series of input, a series of tokens as an input, right? And we are very severely limited by the length of inputs that we can provide as a single sequence. So if this paragraph is like 200 words, for a normal n-gram model to actually have the word Bob even in its context, so if it, for it to even be remotely possible to guess correctly, the length of n should be 202 because it has to stretch down to the word Bob as well, right? And the really interesting thing about, the problem with that, of course, we cannot have an infinite sequence length because it becomes very, very computationally expensive, and words that are towards the end of the attention space, or like the input space, also have contain the least value within sort of an within the latent space of the model. So if I have to represent 200 words with 784 numbers, it is very difficult for me, and what happens is that there is a recency bias that emerges, and only the last few tokens are really represented. So this model is able to sort of escape this problem by creating skip trigrams where the word source may be present way before, or the word perfect may be present well earlier within our token sequence, but when we start to read the destination token R, for instance, it places a focus back onto the word perfect, and we can see the out token, the higher the value, so the darker the value is, the higher the probability of predicting said token, and it's basically creating the skip trigram that we need, where we have the sequence of text in the middle, but it is able to basically say focus on the word Bob and ignore everything else based on the query that we supply who said the statement. Okay, so that's kind of the way it is able to break down the query and identify the keys that it is or the tokens that it is supposed to focus on. And it focuses on Bob, gets us the right answer, everybody's very happy. So this similarly happens for a couple of additional cases. One notable one is for lambda. We can see there are a lot of there are these backslash tokens. This is interesting because this represents latex syntax, and it kind of is understanding the syntax as part of the learning process. Similarly for HTML, NBSP is also no break. I don't remember what it is. Bhavesh, what is NBSP?
Non-breaking space.
Non-breaking space. Thank you so much. So non-breaking space is part of HTML syntax, and it also is able to relate it to HTML syntax. I'm not good with HTML syntax, so I don't super understand that. I can explain the latex part of the question. Yeah.
Why is it called trigram? Where is the tri coming from?
The destination or okay, this is a good question. We have the source token, which is the input, and the okay. So this is very much a guess. Okay, but my interpretation of this is the usage of the word trigram is not the traditional sense of trigram. We have the perfect, which is the original source token, R, which is the destination token, and then perfect, which is the output token. That I assume it is creating or calling a trigram. However, that is not a satisfying explanation to me either. So I'm not sure.
And also for the QK and OE, so there should be a matrix product at the very end to create the logic, right? In the previous slides, it seems there's no matrix product at the very end. So in here, the multi-head attention, they will do the matrix product at the very end, and then goes to the
unembedding.
Yeah.
Yeah.
So but in the previous slides, when you show the circuit, there's no in here. The KTV that matrix, they don't do the.
Oh well, this is just output token from attention. So it's a simplification. The idea is to only focus on the circuit and not the embedding and unembedding steps. Well, actually, unembedding is included as well as embedding. Sorry, I didn't follow. What was the issue?
So in the attention mechanism.
Yeah.
So you will generate the attention weights using the query and key matrix.
Right.
And then at the end, you will do a matrix product with the value matrix, right? And then you will get the final
output. Then final output. And then so these are the two circuits that we obtain from these two equations, right? And the reason we are splitting this, obviously these are interacting, right? We can see that once attention is computed, it interacts with the output and the value matrices as well. So the reason that it is relevant is because we are able to, it's because of another property that we also discussed earlier, where we see that the attention learns independently from the rest of the tensor equation. I guess an analogy that would work well for this case is you have, what do we say? You can consider it like this, alright? You have two students studying at Purdue University. One is majoring in computer science, the other is majoring in music, and both of them are creating a startup that creates generative music, right? They both have their own separate area of expertise. Even though they are learning simultaneously, they are learning two different things. And that's kind of what's happening over here, where attention learns one thing, and the output value transformation learns something that is completely different, even though it is within the same gradient step. And that is something that's really interesting about this entire process as well, which is why we analyze the two of them separately. Does that answer the question?
So there will be two circuits. You break it down into two circuits, right?
Two circuits, exactly. Yes, two circuits. The pink and beige. Okay, awesome. Cool. Any more questions before we move forward? Okay, cool. skip diagram interpretation we discussed. Now, one additional thing that I want to talk about before we move to the next slide is the fact that we notice a lot of cases where there is copying. So the perfect token, when perfect is the source token, we notice that perfect also is the out token. It is basically copying that same input. It is able to detect when the same sort of the word perfect is kind of has to be repeated, right? And similarly, we can see for large, for 2, for lambda, for NDSP, and for grade. All of these cases have copying. Now, this is obviously not representative of all of the samples, but it's like cherry picked for a good reason. And this is something that is very, very prominent behavior that we identify when we try to interpret this as skipgrams or skip diagrams. And we can sort of decompose the fact that this is happening by performing an eigenvalue analysis. So from the definition of eigenvectors, we want a weight matrix or any real matrix that we compute against a vector that only increases the vector by magnitude, correct? And one thing to note is that the eigenvalue that we get can be a complex number, and that will be relevant when we talk about the eigenvalue decomposition, because we have this circle over here. It's basically just the what do we say, a xy coordinate, and x is the real plane, y is the complex plane, and they are just plotting the points. So if any values are present close to the real plane or on the real plane, then there is no complex component. That's a normal real valued eigenvalue. And if there is something over here, or anywhere sort of in the complex space, then the eigenvalue exists, but with a complex component. Now, this is important because all of the values that are present as real valued eigenvalues are the ones that are more relevant to us. If we just randomly initialize the weights, we get eigenvalues just spread randomly throughout the circle. So we also are doing log on the eigenvalues, which is why it is bounded within the circle. But the important thing to note is that out of these 12 heads, we see that 10 of them have the eigenvalues that are very, very dominant towards the positive end of this graph. And this is relevant because it denotes copying. Now, this is not exactly copying, but it is more so copying on average. Still, it is a very important sort of demarcator of the fact that some copying is taking place. The reason for that is that having a positive sort of set of eigenvalues over here kind of reflects how likely the same token is to have a high probability if the same token is the input. Conversely, if we have very negative real valued eigenvalues, what would be happening is the existence of source token perfect would reduce the probability of perfect also being the output token. So that is something to keep in mind. We don't see that behavior at all. A lot of the behavior is centered around copying. And there is also a 2-layer eigenvalue analysis that these guys have done for the transformer circuits paper. We won't go through it, but this also it also sort of further emphasizes the copying behavior that we see. Cool. So that was circuit analysis. Now, yes, question.
So when the picture mentions eigenvalue analysis of first layer of custom head circuits,
Yeah.
is there a pattern as it goes through the different layers of the transformer? Does the behavior of the eigenvalues change?
Yes, so the behavior of the eigenvalues becomes even more dominant towards copying. So we see that there is this high amount of variance over here, right? The variance is reducing from the left all the way to the right. So for the second layer, right, which we are not actually showing here discussing today, the emphasis for the variance of the eigenvalues that we got was even more centered towards the positive real numbers, which kind of shows that we are also copying very frequently. And also the reason I said that it's copying on average and not exactly copying is if it is copying, if the tokens appear positive with a delta. So for example, if I see the word Bob and the word said has a high probability of being repeated, that also technically counts as positive eigenvalue, and that will be very, very close to what we are seeing over here. So on average, we notice that, of course, for the cases with the least variance, we are most sure that it is copying the direct token itself. Question?
So why the so if the eigenvalue is a real number towards the on the right hand side, why does it mean a copy operation? And by copy operation, do you mean copy the whole V matrix?
It is not. It copies. It doesn't copy the OV matrix. So OV transformation is different. The eigenvalue decomposition for the real for the real component being very, very heavily shifted towards the positive is a important reference for copying, because I'm not going to be able to give you the most satisfying answer, but this is the line on top. When we map a vector space onto itself, the eigenvalue analysis is effectively that, like, they were able to demonstrate the fact that the copying exists when we evaluate eigenspaces for a vector space mapped onto itself.
And copy what? Copy.
Let's say we have source token perfect, right? We have the R over here, which is our destination token, and then we have the output token. The probability of this being perfect is very high when the eigenvalues are positive and non-complex. When the values are negative and non-complex, then the value, the likelihood of the output token being, or the log for the output token being perfect is opposite. It's low. It's very low, and otherwise it's somewhere in between. It's random.
So it's copying the token?
Yes, it is copying the token. Okay. Any more questions? No. Okay. Cool. So let's talk about monosemanticity, which is again a very, very cool idea. I had a demo, but I don't think we'll be able to cover that. Let's not worry about that now. Anyways, to start off, is anyone familiar with the curse of dimensionality? Yes.
Oh, pushpin.
Yeah.
Oh, okay. It's like when you have in your input size is like the dimension is extremely large. You need either a lot of data points to sort of in a layer clustering sense to cluster them together. Otherwise, the input doesn't really represent any observable pattern.
Right. That is not the specific one that I was talking about, so I'll just reveal it. For our current case, the curse of dimensionality is basically the amount of features that are represented is directly proportional, or the amount of latent space that we have to imagine is directly proportional to our layers, and this is polynomially related, so we have C is any constant, and so if we add two layers, it is not a linear increase of latent space, it is a polynomial increase in our latent space. Now, this is a problem because it makes it very difficult for us to analyze it at scale. And in addition, this is not something we would typically consider a problem, but for interpretability, this is something that becomes a huge issue. So, neural networks are incredibly efficient at compressing information, right? We give it, say, 1 million parameters, and it is able to embed information that is much more than what we could sort of talk about or display with just 1 million tokens. And the reason for that is the principle of superposition, but not superposition as it relates to physics, superposition as it relates to neural networks. This is something that Anthropic has defined. So the idea is that if you were to disentangle a model representing every individual features, we would get something that is incredibly larger than the input set that we have currently. And that is a problem because certain things fire where it makes absolutely zero sense for us to fire. So if we were to sort of do a breakdown of the features that a specific neuron would hit, like just any theoretical neuron, right? We can imagine that this neuron fires for cars as well as the nose of a dog, right? And this is something that doesn't make sense to us intuitively because we want a neuron to be decomposed into a very specific feature so that we are able to identify when something is behaving in a particular way. And superposition basically means that we are not able to do that at the benefit of a much higher accuracy. So it's not interpretable, but it is very, very accurate. And when we analyze these individual neurons, it fires in unrelated concepts, which is what I was talking about. And in this context, it is called polysemanticity. So before this, we were discussing the architecture of the transformer. We were using a single attention layer, right? Now we are going to upgrade that. We are not able to analyze MLPs mathematically. So instead, what we'll do is we'll analyze them empirically. We have this original architecture that we had before, but over here in the middle, we create this MLP and run ReLU activations. And these ReLU activations are very, very important to us because these are what we will break down and analyze using an overcomplete sparse autoencoder, and I will explain what that is in just a second. But this is the regular architecture. Fundamentally, this is the smallest language model that we do not fully understand. And this paper seeks to break down the specifics behind this specific architecture. So the way that the authors set up training was by creating two models. The first was a transformer model. This is what we want to analyze. And one is a sparse autoencoder, which is basically placing a model against itself and asking it to interpret the features that are present or break down the polysemantic features into monosemantic features. Monosemantic features basically means we want each neuron to only show one specific thing. So we have the architecture for the transformer, which is basically the diagram that we have described earlier. The MLP size is 512, which is a bit relevant. And the data set is the Pine, it is 100 billion tokens. They discovered empirically that the larger the data set size, the more interpretable were the features that they were able to extract. So that is relevant, and we use autoregressive log likelihood in order to just train the model on the Pine task. The sparse autoencoder is trying to reconstruct the activations by expanding the input from a value of size 512 to something that is a factor of 512. So for instance, if I have the activations, I will basically treat these activations as a single sample. I then move the these activations into an autoencoder. Now normally an autoencoder would be compressing the 512 to maybe 24 or something similar to that. But in this case, we want to make it overcomplete, in which case we are basically going to make this layer larger than that of the input and then again recompress it. The idea is that we want to generate a sparse representation of this 512 token sequence or the 512 vector. If we batch this will be like n comma 512 to n comma 512, which is more like the regular training setup that you may be familiar with. But for purposes of analysis, we can just consider a batch size 1. That's okay. So we want to create. This is not 512. This is 512, and this is say n comma 512 times 8, because that's what we are currently analyzing. So we create this. Excuse the bad art. But we are creating this sparse overcomplete autoencoder and basically training it in order to generate sparse representations that create features that are fundamentally interpretable. So that is our objective. We are creating a transformation from polysemantic features that fire for random things to monosemantic features that fire for some certain very, very specific things. Question?
So the idea is to try to make a neuron only activate once. For one task, not for another task.
Kind of. So that is the ultimate kind of end goal, right? That would be if we were to analyze it at the architecture level. So if we were to make sure that, or if we were to enforce that during training of the transformer architecture, the neurons remain monosemantic. This will have a caveat of the accuracy being lower, and even though that is technically the case, these authors considered that approach originally. But they found out, for reasons they do not explicitly specify, that it is not possible to obtain a neural network that is fundamentally monosemantic. So this is a post hoc process that the sparse autoencoder is doing after the transformer architecture is already trained.
And what is the F? The NLP size, 5, 12?
Oh, F is a factor, and factor is between 1 and 256, so it's expanding it. It's either exactly the same as the input of the MLP size, or expanding it by a factor of 1 to 256. And for our analysis, we use F as 8.
And what is the, to the order of 5, what is 5 there?
Oh, that's a footnote. Sorry.
Oh, okay, sure.
Cool.
How does the analysis change as that goes from like 1 to 256?
So there is this property of feature splitting. So we'll talk about actually decomposing the features, and then I'll talk a bit more about feature splitting. Even though it's not in the slides, it's really interesting. It basically the features that we are able to obtain can be clustered using UMAP, which is like principal component analysis. It reduces the dimensionality of the input or of the feature that we obtain, and we are able to identify clusters for certain things. And the more features we create, the more clusters, the more data points exist at a particular cluster center, where it kind of like a decision tree. You have certain splits that we are creating, right? The deeper the tree is, the more splits you create. It's kind of like that, where it is decomposing a feature into subfeatures, into subfeatures, into subfeatures, based on the number of the values that are there within the MLP of the sparse autoencoder. Okay. Cool. Question.
What is the L2 reconstruction?
L2 reconstruction is the loss that is used to gain to identify the output. I'll talk about that in a second. So we'll get to the training of the sparse autoencoder. More details has the L2 reconstruction loss as well. Cool. Sparse, because we are constraining the sparse autoencoder. The sparse overcomplete autoencoder is trained against the objective of making polysemantic activations monosemantic features, and the reason that we use the word sparse is because we are constraining activations for the hidden layer only using L1 penalty, and overcomplete because the hidden layer exceeds the input dimension. Okay, so sparse dictionary learning, this is our formula for L2 loss. Given X, which is our data set, we want to create a dictionary with keys D and values, or keys D and values R. This is Wikipedia definition. I should have probably changed it, that's my bad. But we want to minimize the loss between DR, which is basically the output of the final matrix computation. We're subtracting X by what we want to obtain, and we want that to be as close to 0 as possible. We have sub F over there for the L2 norm. So the definition for that, now these people used L2 norm specifically, so you can consider F is equal to 2. But the F that was used over here was for, what is it called? Okay, I don't remember what the thing was called, but it was basically some very specific number that has certain properties that are interesting. I did not understand even a little bit of why the number was what it was, but I will share a link later on for you guys to check out. Anyways, this is our objective function that we want to minimize, and we can motivate this transformation by creating this X raised to J, which is the activation of the hidden layer. We want to make it basically equivalent to the feature times D over all of the features that we want, and adding our bytes. This is just for training.
What is dictionary learning again?
Oh, okay. We are creating this dictionary, like we want to obtain D and R, which are two matrices, right? This is effectively our dictionary. And this dictionary is completely learned from the input using reconstruction loss. And the breakdown for the dictionary is important because the keys for the dictionary that we obtain within D sub I refer to directions within the features. And I will show you a nice example of that in a second.
You mean the dictionary is the R with dimension of D?
Dictionary is D with a dimension of R is to D times N.
Oh, which one?
D. D is
D.
the keys. D is the keys. D are combined is the dictionary.
Oh, the R.
R is representations or keys. Values.
Okay, D is the keys and
Yeah.
R is the value.
Yeah. And we have this representation of the entire training process relevant for our training case. But the idea behind this or the intuition behind this is something that you probably already have seen before. If you all remember the example with the word embeddings vector arithmetic, where you have king plus like a king vector plus what is it, plus woman, and it equals queen, right? This was a sort of a representation that we were able to obtain with vector arithmetic, where we obtained a vector for king and a vector for woman, and we added this to create a new vector. And what we identified was that the main difference for the king and the woman was along only a single or small set of only a small set of elements within the vector representation. So let's say this is fully cleared and with a hole over here in the center, and this is just fully dark. Okay, so this specific bit over here, right, which went from dark to light, is kind of the direction of the feature, and this direction effectively represents gender, right? So we can posit that this tiny thing over here is representative of gender. Now this is an example where a unit value creates or uses a feature that is interpretable to us, and that is why it is something that we can easily identify or say that, oh, this is something that's useful, right? And most cases you will not see something like this, and that is why we basically use the sparse autoencoder to create all of these directions and perform automated as well as manual analyses on these directions that allows us to identify certain interesting features within the model that is in some cases completely covered, and we basically cannot see it at all in our practical interpretation. Some interesting implementation notes, these are not super important. The B sub D is for the decoder for the autoencoder setup. They tie it with the final output to only use to kind of nullify this. The reason that they gave is that it is completely empirical, it improves performance, and they did not talk too much about it as far as I read at the very least. There is also the problem of dead neurons, where we have the ReLU activation. So if anything is if any values exist within ReLU that is below 0, the formula is basically just max of 0 or x. So if any value exists below 0, so y. So if x is equal to -1, y is equal to 0. If x is equal to 1, y is equal to 1, right? Now, if the values are extremely negative, what happens is that y always becomes 0 because it is so negative, and the result is that these neurons die. And the way that the neurons are kind of resampled is by just giving it a random weight, when after a certain set of batches the value of y stays 0 and it just does not update. Cool. So that's sparse dictionary learning. To evaluate the interpretability of the features, they created a rubric from 0 through 14 and asked manual human evaluators to identify how interpretable certain features were. Word 8 was a threshold that was that was kind of arbitrarily chosen and identified to be significantly interpretable. And for the automated interpretability, they basically told a language model to evaluate how interpretable this feature is based on the input that we give you as well as the rubric as a reference. And this was normalized with a maximum of 1, and I am not sure why it goes below 0. I thought it was normalized between 0 and 1, but I guess that is, oh, this correlation, which is why it goes between 1 and -1. So that's experiment correlation that it is normalized to, and the general idea is that the more values that exist towards the right, the more interpretable certain features are, and the features that we were able to decompose from the sparse autoencoder are in pink. The blue values are just the empty neurons, or just the activation outputs, and we can see that in general the activation outputs are significantly less interpretable than that of the features that we get from the sparse autoencoder. We will talk about a specific case, but before that, your question.
How was the dictionary learning related to the over complete autoencoding?
So we are trying to train, or we are trying to create a dictionary from the input space, and this dictionary contains weights that.
Can you use it as a loss function? You have a L2 loss x, right? X minus dr.
Yeah, you can just consider fs2, and yeah, that would be a loss.
So how is that related to the autoencoding?
That's the objective function that we want to minimize. So the autoencoder, the L2 reconstruction loss, that is the value that is computed after x. We randomly initialize. We already have x. This is predefined. We have dr, and we do x minus dr, calculate L2 norm of it, and then that's our loss value, right? When we square the L2 norm, and that's our loss value. Then we backpropagate against it to minimize the loss value, and at which point we have minimized the loss value is when our model is trained. So we have a trained sparse autoencoder, then those features we can sort of look at and say, oh, this is interpretable, that's good.
And how was that translating into the graph?
So we have the pink values and the blue values, and the purple is overlap between the two, of course. And the human evaluator looks at all of the features. It looks at all of the neurons and compared, basically did a blind taste test almost. He was given a value and an explanation, and he rated the explanation between 0 through 15 or 16, and the higher the value, the better it was.
Explanation of what?
Explanation of the specific feature, or of the specific behavior. Behavior of what you're finding. Yeah, I'll show you a specific example in a second. But this is kind of like the high level of it. Yes.
I'm trying to understand why the sparse autoencoder works. So if you take your initial set of features and you send it to this sparse your second layer, does that just make the feature direction sort of more evident because you have more neurons to work with?
It's for two reasons. So firstly, we enforce sparsity by the L1 loss on the hidden activation of the sparse autoencoder. So this over here we are running L1 loss on. Okay, so we have that component that enforces sparsity. Okay, and L2 for reconstruction. Of course, these two things basically achieve the opposite of the transformation over here, right? We normally have this observer model that is small but can be decomposed into a lot of weights. The sparse autoencoder is decomposing this polysemantic model into a set of monosemantic features, and these are the features that we are examining.
Oh, I see. Okay.
Awesome. Cool. And do we have any more questions? Also, I know we're almost 5 minutes past, but I'll speed through this a little bit. So stay with me here. So I wanted to analyze A13450 that fires an Arabic script, but again, we will go a little bit quick here. But this feature is effectively invisible when we view it through the polysemantic model. In that sense, in the sense that the feature is almost like a linear combination of other neurons, and it cannot really be observed individually in a fashion that makes sense to us. And it is able to identify the specific Arabic script through the sparse autoencoder. Now we evaluate the probability of the token using the log likelihood ratio. We just compute log of a token given we have Arabic text and the token on an absolute log. Like we plot the histogram against all of the tokens, and we observe something very, very interesting. So in our training data, Arabic text consists of only 0.13% of the set. Right? We have 200 billion tokens. Out of that, only 0.13% is actually Arabic script. Despite that, 81% of active tokens are sort of subsetted to the Arabic script, and this is because of the sparse autoencoder, in the sense that it is attending to other text within Arabic because the input text exists in Arabic. So we can see like a series of text here. It is not super sharp. I apologize for that. But the deeper the value, or like the deeper the color, the higher the attention is placed on that specific value. And we can see towards the left, we have text that is Shah the copyright, and it's super dim. And we have text that is Arabic towards the right that I cannot read, but it is very sharp, or has a very, very high value. So despite the fact that we would not expect it to have a lot of focus because of how backpropagation trains to ignore certain tokens in order to get the highest possible net value or the net metric that it's trying to optimize, with this approach we are able to identify only the subset of tokens within the specific script based on the activation of a specific feature and not that of a neuron. And we can use this to like extend it, where we force a certain feature to have a high value, and that causes the generation of the specific type of text. So we have this input over here. We are just entering numbers from 1 through 10 with zero intervention. It outputs another set of numbers. But if we force the values for Han Chinese, base 64, DNA, uppercase, hexadecimal, Arabic or Hebrew, it basically outputs that specific type of feature with the exact same input numbers from 1 through 10, which is kind of insane. So that's monosemanticity. The approach set high values of features of the desired behavior that we want, which is what I said. And importantly, we also observe that interpreted features that we talk about here are actively used by the model. So this is not just a post hoc visualization of the approach. It actually represents the information that the model uses in order to make its final prediction, which is what interpretability is all about, which is awesome.
The generation on the right hand side, how is it related to the autoencoder?
So the autoencoder processes features at the activation of the NLP, correct? After that, we still have the unembedding token that is left, that is completely not interactive. So what we are doing is we are forcing the features to have a very high value for for features for Han Chinese, for instance, we force that to have a value that is very, very high, and the consequence of that can be observed in the downstream inference of the task, wherein all of the neurons that relate to Han Chinese that we obtain from highlighting only specific feature A1 2000 creates characters that are only Chinese, that forces the generation of characters that are only within Han Chinese.
So the autoencoder is embedded into the language model?
The autoencoder is not embedded into the language model, but when we try to use this spin feature sampling, what we are doing is we are interrupting the execution of the language model, running the sparse autoencoder, then using the output from that in order to continue the rest of the downstream prediction. It's like if I were to use GDB to break a program, change a variable, and then
open
continue.
inside, and then you take embedding, and then you use autoencoder to generate the output, and then plug it back.
Yeah, with the pin feature. So regardless of what certain neurons are fired at, we force set them to be high, and then we can sample it.
So you have the...
We are overwriting values, basically. Overwriting values in memory. If that's a good enough analogy. Awesome. Cool. So the last thing that I will talk about today is finite state automaton, which is another thing that kind of is a part of what the pin feature sampling feature is, wherein the unique a unique thing that we notice is, ignore my broken English in the first sentence, but a unique feature that we observe within this setup is that certain things behave, or like certain features behave like finite state automaton, wherein it's not traditional circuits like we discussed earlier, but it kind of makes a following token or a following type of token have a very high probability, which makes another token have a high probability, and it kind of goes through that Lego chain wherein the next token has high probability and so on and so forth, and it tends to generate text that is very, very similar. So it is what leads to the notion of memorization within transformers. It is partially explained by this behavior where it generates this certain subset of text every single time, and it's kind of like an element within HTML where it creates an undefined list, adds value, adds data within it, closes the undefined list. Both of these chunks of creating and closing the undefined list is part of a finite state automaton that starts from creating a greater than sign, typing UL, closing the greater than sign, and then the backslash for when we are closing the undefined list as well. So this can be interpreted as a finite state automaton where one thing leads to the other, leads to the other, and so on. And that's the final sort of very, very interesting thing that they have talked about. We still haven't really even scratched the surface with this thing. There are huge things that I've kind of just ended up omitting, including the reimplementation. I will share the link for that with you if you'd like to check it out as well. But this is all that I have to talk about. Thank you so much for sticking around. Slide links are there over there as well as in the Discord. Have a great rest of your day.